Hello and welcome to this Volkswagen Communication Network service release. Today we'll look at the new Digifant fuel and ignition system. Volkswagen developed the new and unique Digifant system to provide optimum engine fuel and ignition system control throughout the entire range of driving conditions. This results in improved drivability, excellent acceleration, and more efficient operation. In today's program, we'll see how system components supply engine operating information to a single Digifant control unit. We'll look at how the control unit processes the inputs from various engine sensors to provide precise fuel system operation and optimum ignition system operation. Then we'll demonstrate basic system checks and adjustments and conclude by performing tests on some of the system's individual components. To help you understand how Digifant operates, we'll look at the fuel injection and ignition systems separately. Let's begin with the Digifant fuel system. An electric fuel pump delivers fuel to the fuel injectors. A double-arm pressure regulator maintains the desired system fuel pressure to all the injectors by controlling the amount of fuel returned to the fuel tank. The regulator varies the amount of fuel return based on intake manifold vacuum. Here's how this happens. An engine under light load has high intake manifold vacuum. The vacuum pulls the diaphragm away from the return port, where the fuel flows out of the regulator and back to the fuel tank. The diaphragm moves away, allowing enough fuel to return to the fuel tank to maintain the desired fuel pressure to the injectors. An engine under full throttle or high engine load has low intake manifold vacuum. This allows the spring to move the diaphragm closer to the fuel return port. This in turn reduces the flow of fuel back to the fuel tank and increases fuel pressure to the injectors, creating a richer mixture to match the increased fuel demand requirements. When the injectors receive an electrical signal from the control unit, they open and spray fuel into the intake port near the intake valve. The Digifant control unit determines the basic fuel injection rate, or length of time the fuel injectors are open. It does this by processing information on engine load from the airflow sensor and engine speed from the hall sender in the distributor. The control unit compares signals from these two components with values stored in the control unit's fuel injection memory at 256 fixed points. So, based on the inputs from these two sensors, the control unit can determine the length of time that the injectors remain open, and therefore how much fuel is delivered. Now let's look at these two components individually. The central component of the Digifant system is the airflow sensor. The airflow sensor sends a variable voltage signal to the control unit based on quantity of air entering the intake manifold. This signal indicates the amount of engine load. Airflow through the sensor opens the sensor flap against spring pressure. The movement of the airflow sensor flap actuates a potentiometer in the sensor flap housing and determines the voltage signal which is sent to the control unit. A compensation flap dampens out pulsations in airflow to provide a smooth, steady signal. The control unit then calculates engine speed based on a signal from the hall sender. The hall sender consists of a semiconductor layer placed in a magnetic field. An air gap separates the semiconductor layer from the source of the magnetic field, a permanent magnet. The magnetic field deflects some of the electrons in the semiconductor to one side, creating a voltage across the semiconductor. The control unit receives this voltage, known as the hall voltage. When the trigger wheel is not in the air gap, the magnetic field penetrates the semiconductor layer, generating this hall voltage. When the trigger wheel shutter enters the air gap and blocks the magnetic field, the hall sender no longer generates the hall voltage and is switched off. As the distributor turns the trigger wheel, the control unit uses the hall sender's fluctuating on and off voltage signals to determine engine speed. The signals from the hall sender and the airflow sensor provide the control unit with information to determine basic fuel injection rate. The Digifant control unit modifies the basic injection rate based on 4 additional correction variables. In this way, it provides for smooth and efficient running characteristics throughout the full range of engine operation. These variables in engine operation are engine temperature, intake air temperature, throttle position, and oxygen content of the exhaust. Let's look at these 4 variables individually. Cold starting and cold running are vitally important to engine operation and drivability. The coolant temperature sensor in the thermostat housing signals the control unit to provide cold starting injection and to increase fuel quantity during cold engine operation. This eliminates the need for a cold start valve and thermal time switch. Based on signals from this sensor, the control unit then gradually decreases the injection quantity as the engine approaches normal operating temperature. This assures smooth performance during the critical warm-up period. The intake air temperature sensor, located in the airflow sensor housing, transmits a signal to the Digifant control unit based on the intake air temperature. The control unit uses this signal to change the basic fuel injection rate based on variations in the temperature of the incoming air, and is used to determine the fuel injection rate during hot starting. The position of the combination idle and full throttle switch, located under the throttle housing, signals the control unit to either provide a richer mixture during full throttle operation or shut the fuel injectors off during deceleration when the throttle is closed to improve fuel economy and reduce emissions. Once the engine reaches operating temperature, the oxygen sensor measures the oxygen content in the exhaust gas ahead of the catalytic converter and sends a corresponding voltage signal to the control unit. The control unit processes this signal and makes minor adjustments to the opening duration of the injectors to maintain the desired air-fuel ratio. By using the information supplied from all of these sensors, the control unit constantly adjusts and maintains the precise fuel injection rate over the full engine operating range during cold starting, normal operation, and hot starting under all engine load conditions from idle to full throttle and closed throttle. Because the new Digifant system combines the Digijet fuel injection system and the map-controlled electronic ignition system, some of the same sensors that provide information for fuel injection quantity also provide information for ignition timing. The ignition system determines ignition timing from a map programmed into the control unit's memory. To determine the ignition timing point, the control unit uses the information it receives about engine load and engine speed. The control unit processes these signals and determines ignition timing by providing a signal to terminal 1 of the ignition coil. As with fuel injection control, the air sensor flap provides information on engine load, and the hall sender in the distributor provides engine speed information. These 2 inputs to the control unit determine the basic ignition timing at 256 fixed points. In addition, the coolant temperature sensor provides information used to modify the basic timing during cold starting and warm-up. As with fuel injection, the signals provided by the engine coolant temperature sensor allow the control unit to tailor the ignition point to the precise needs of the engine. Now that we've seen how information is supplied to the Digifant control unit and how it determines ignition timing points and fuel injector opening duration, let's make some of the basic checks and adjustments which are part of routine maintenance and are also the first steps in problem diagnosis. During this demonstration, we'll check the ignition timing, idle speed, and CO, or carbon monoxide content of the exhaust. Begin by connecting the VAG 1367 tester to the engine and the exhaust gas analyzer probe to the exhaust pipe ahead of the catalytic converter. Start the engine and allow it to run until it reaches normal operating temperature. You may have to rev the engine above 3,000 RPMs and allow it to return to idle. This ensures that the VAG tester receives an accurate timing and RPM signal for its display. To check the ignition timing, disconnect the coolant temperature sensor in the thermostat housing and run the engine at 3,500 RPMs. Ignition timing should read 5 degrees before top dead center, within a range of plus or minus 2 degrees. By running the engine at 3,500 RPMs, the timing is allowed to stabilize. With the coolant temperature sensor disconnected, it no longer provides information to the control unit. Without this signal, ignition timing remains at a fixed point, which has been programmed into the control unit's memory. The Digifant system uses an idle stabilization valve and separate idle stabilization control unit to maintain engine idle speed at a constant level during all engine operating conditions. If engine speed deviates from the specified RPM value stored in the idle stabilization control unit's memory, the valve opens or closes to change the quantity of air bypassing the throttle plate. If, for example, idle speed is too slow, the control unit increases the current to the valve, making it open and increasing airflow. This opens the airflow sensor flap wider and increases idle speed. In addition, this system of idle stabilization also provides increased idle speed for a cold engine or an engine under extra load. For example, in a cold engine, the idle stabilization system receives a signal from the coolant temperature sensor to increase engine RPM to overcome internal frictional resistance. Similarly, when the steering is at full lock, the power steering pressure switch signals for increased RPM to compensate for the additional load. The idle speed also increases when the automatic transmission is in gear or the air conditioning clutch is engaged. Let's return to our basic system checks and measure engine idle speed. Before starting the engine, disconnect the Terminal 1 wire connector to the idle stabilization control unit. With Terminal 1 disconnected, the idle stabilization valve receives a fixed milliampere signal and remains at a predetermined position. Connect adapter VW1315A2 between the idle stabilization valve and the wiring connector. Use an ammeter switched to the 2 amp scale to verify that the correct current is supplied to the idle stabilization valve. Now, start the engine. The reading on the ammeter should remain at a fixed value and match the published specification. Remember, when Terminal 1 of the control unit remains connected, the engine RPM will not change when the idle speed screw is turned. The idle stabilization control system automatically compensates for changes in idle speed to electronically match the value stored in the control unit's memory. This system of idle control eliminates the auxiliary air regulator, the digital idle stabilizer, and any periodic idle adjustments. The use of this new system results in extremely precise idle regulation that can vary idle speed to match engine requirements. The last of our basic checks is for carbon monoxide, or CO content, in the exhaust. To perform this test, switch the ignition off, then disconnect the oxygen sensor lead wire. With the exhaust probe connected ahead of the catalytic converter, restart the engine and measure the carbon monoxide percentage in the exhaust with the exhaust gas analyzer. It should be within published specifications. If it's out of specification, adjust the idle mixture by first removing the plug from the airflow sensor housing. Then adjust the mixture screw until the specified value is obtained. After making your adjustment, be sure to recheck idle speed and ignition timing to ensure they have not changed. In the final part of our program, we'll go through the procedures for checking individual components. This should prove helpful in the event you need to diagnose an engine performance problem. First, check to be certain that all ground connections are secure, Especially, check the ground stud on the cylinder head. Check the wiring connector at the Digifant control unit and all the other Digifant sensor connectors to the control unit, the coolant temperature sensor, fuel injectors, hall sender, throttle switch, oxygen sensor, and oxygen sensor heater. In addition, check the idle stabilization control valve and the idle stabilization control unit. If the vehicle is so equipped, check the air conditioning clutch, power steering pressure switch, and automatic transmission inputs. Next, check the airflow sensor to be sure it moves smoothly. A sticking or rough operating sensor flap will cause poor running. Remember, the air flap position provides information for the basic fuel injection rate and ignition timing. You should also check the operation of the air temperature sensor. To do this, connect an ohmmeter across the terminals on the airflow sensor housing and read the resistance value. Refer to the wiring diagram to ensure you have the correct terminal numbers for this test. Compare the meter reading to the chart provided in the latest service repair information. This sensor is referred to as an NTC, or negative temperature coefficient resistor. This means that the resistance value varies inversely with temperature, decreasing as air temperature increases. If the resistance reading falls outside the specified range, the entire airflow sensor needs replacing. Be sure the electrical connector at the airflow sensor is secure. If the airflow sensor sends no signal, the engine will not run. With an ohmmeter, check the resistance of the coolant temperature sensor in the coolant thermostat housing. This sensor is also a negative temperature coefficient, NTC, resistor. If its resistance does not fall within specification, replace it. The coolant temperature sensor provides important information for the control unit to calculate both ignition timing and fuel injection rate. The control unit has a special override feature in the event the coolant temperature sensor fails. If the coolant sensor becomes open-circuited, the carbon monoxide percentage in the exhaust gas will rise to a predetermined value, which allows driving the vehicle to a service facility. Finally, check the operation of the throttle switch. This switch is actually two separate switches connected in parallel. They provide a signal for enriching the fuel mixture when the engine is operating at full throttle and determine fuel shutoff characteristics during deceleration. To test the operation of these switches, connect an ohmmeter across the two switch terminals at the wiring connector. With the throttle closed, the meter should read 0 ohms. Open the throttle plate. The ohmmeter should go immediately to infinity ohms. Continue to open the throttle. As you approach full open position, the full throttle contacts close, and the ohmmeter should once again read 0 ohms. If the idle full throttle switch is open at idle, frequent stalling will result during cold engine operation. In addition, the deceleration fuel shutoff feature will not operate. If the switch remains closed when the throttle plate opens, the engine will surge between speeds of about 1,500 to 1,700 RPM. Finally, if the switch does not close at full throttle, no fuel enrichment will occur and power output will be low. You can also check the operation of the fuel pressure regulator. Remember, the pressure regulator maintains a constant pressure to all the injectors. To check the regulator, connect a fuel pressure gauge and adapter VW1318/17 to the fuel pressure connection port. Then start the engine. Fuel pressure should read about 2 bar. Disconnect and plug the vacuum hose to the regulator. Pressure should rise to between 2.3 and 2.7 bar. This increase in pressure means more fuel will be injected when manifold vacuum is low, such as under high load conditions. As part of your checks, be sure to look for leaking vacuum hoses or connections. An intake manifold vacuum leak will result in excessive fuel enrichment, leading to higher fuel consumption, plug fouling and low power. Recheck the hose connection to the pressure regulator to be sure it's secure. If this vacuum hose has a leak, replace it. This concludes our demonstration of the Digifant fuel and ignition system. In this program, we've given you basic background information, including an overview of the fuel system, pointing out the interrelationship of components. We discussed fuel system operation, ignition system operation, basic checks and adjustments, and concluded by testing some of the individual inputs and components. This program and the additional service information provided will enable you to keep current with the latest diagnosis and repair procedures for this advanced system.